Good day to everyone. So in this video, we are going to see about the heat conduction equation and how to solve this heat conduction equation using the finite difference method. So how to write the differential equation, partial differential equation for the heat conduction equation. Let us consider a long rod with the length of L, and the starting point is taken as x is equal to 0, and the other point is taken as x is equal to L, and so the length of the rod is taken as L. Suppose if you consider the rod is having the source of heat, and the rod may be heated at one end of this one end, or either of the ends, whether at x is equal to 0 or x is equal to L, or any point in the middle of the rod. Suppose if you apply a heat, then the heat will spread out through the metal rod, because the bar is insulated, so that the heat conduction for the environment is actually forbidden. So the heat will actually only conducted through only into this rod from the source point. Suppose if you consider the u of x comma t is actually the temperature of the rod in any instant of time t in any point of this rod, then the problem is to be study the flow of the heat in the rod. Okay. So the partial differential equation is governing this flow of the heat in this rod is actually given by the equation of u of t, which is equal to c squared into u xx, which is nothing but the dou u by dou t, which is equal to some c squared into dou squared u by dou x squared. Okay, so here u is actually referring the temperature, and how this temperature is actually varying with respect to time and the space x. This is this equation is governing the heat conduction equation. So the limits for the x is given as 0 to L is the limit for the x at any time of t greater than 0. So here the c squared is nothing but the constant, which is actually depending upon the material property of the corresponding rod. Suppose if you are using iron rod or copper rod, then the spreading of heat from the source point to other point is actually differs for the different materials. So that is actually defined by the constant c squared. So in order to find the solution of this problem, then we need we actually have the unique solution, and then we have to require the different conditions to solve this equation. One is the initial condition. So the initial condition. So the initial conditions are something is actually given when time t equal to 0. So for time t equal to 0, the temperature prescribed at the source point is taken as u of x comma 0, which is equal to some function of x. Okay, since we already know that the x is actually varying from 0 to L. So this is the initial condition. At time equal to 0, we have the some function of x, which is actually defining the initial condition of the given rod. Okay, that means the initial temperature. And since the bar is having the length of 0 to L, we can also give the boundary conditions also. So the boundary conditions are, suppose the bar is actually having the length of L, the boundary conditions at x is equal to 0 and x is equal to L you can give, because for at x is equal to 0, that is one end of the bar, we may have some temperature or a condition, and similarly on the another end also we have the variation of temperature which we have, so that if you given the values of x is equal to 0 and x is equal to L, that is the boundary conditions of the given rod. So you can give these boundary conditions in two different following types. One is suppose if you consider the temperature at the end of the bar can be prescribed by u of 0 comma t, which is equal to some g of t. That means that at x is equal to 0, you can give the u of 0 comma t is equal to g of t. Similarly, at u of L comma t, which is equal to some h of t. So these are all the two boundary conditions which is given for t greater than 0. Okay, or in some case, if the any one of the end is actually insulator, then we may have the different boundary conditions. So the second type of boundary condition is, let's say at x is equal to 0 is actually insulated point, then this dou u by dou x is equal to also E0, and x is equal to 0 for all the time. because of this insulation, so that the boundary condition at the one point is actually given as 0. At the same time, at the another end of this bar, the temperature can be prescribed as U of L comma T, which is equal to some H of T for all the values of T greater than 0. So this is actually L comma T. So this U of L comma T is the condition for the another end, or you can just reverse it. You can just insulate a point at Lx is equal to N. You can insulate the rod so that this condition is actually interchanged for the that kind of cases. Okay. Therefore, if you look into this the heat conduction equation, it may be a initial condition problem or a boundary value problem. So since both the initial conditions as well as the boundary conditions are given, so you can either consider this as an initial value problem or a boundary value problem. Since for our study we are actually considering this is the heat conduction equation as a boundary value problem, and we are going to solve this boundary value problem using the finite difference method. Okay. So the finite difference method which we are going to use to solve this equation is actually is same as what we have studied in the last lectures and videos. So we have having the same finite difference method, but here you can see this the temperature is actually varying with respect to time as well as the space. Both are different quantities, so that the time is actually varying with respect to the time is actually varying with different fashion, and the space is also varying with respect to different fashion, so that we can actually superimpose this domain of x is actually in between from 0 to L for all the time into a rectangular network of mesh points, because this so in y-axis actually the time is actually varying, and in x-axis we are actually varying the space, so that the t is not actually equal to x, so that we always have the rectangular kind of mesh points in the interval of 0 to L, which can be divided into uniform intervals of some m equal parts, let's say, and so each mesh points in this x-axis can be written as, suppose if it takes the h, if we take the mesh point count as h in x-axis, is given by the total length L divided by m. So that is the total number of mesh points which we have got. Therefore, the mesh points along the x-axis can be written as xi, which is equal to some I times of h, where the I is runs from 0, 1, 2 up to the mth value. And similarly, you can divide mesh points in the y-axis for the time t, which is actually given as some tj, which is equal to some j times of k, where this k is j is actually runs from again 0 to 1. So the combinedly, so each mesh point is actually having the values of some x of I comma t of j in any point in this space of x and t, and we call this tj is the jth time of the interval. Similarly, the x is for the I and j is actually representing the increment of both x and t respectively. So at any point of x of I comma t comma j, we denote the numerical solution by u of I comma j. So this is actually equivalent to the x of I comma t comma x of xi comma t j, which is actually giving the exact solution of this, the numerical solution of this point, and the corresponding exact solution of this point can be written as u of xi comma tj. Okay, fine. So suppose if you want to solve this heat conduction equation, we are going to use the finite difference method, and we have the two different classified two different categories of finite difference method are used to calculate, used to solve this heat conduction equation. One is the explicit method, which is also known as the Schmidt's method. So this explicit method is actually known as the Schmidt method. The next one is the implicit method, which is also known as the Crank-Nicholson method. Okay. So we are going to see how this heat conduction equation is solved using the both explicit as well as implicit methods. So in the explicit method, the solution of each nodal point of this the problem is actually obtained by just simple computation of any arithmetic operation using the solutions of the previous or more levels, which is actually more levels which we have calculated using the numerical method. However, in the implicit method, we are actually solving this linear system of algebraic equation for all the unknowns on any point of t equal to some t plus j plus 1. Suppose if you are using the implicit method and we use the nodal values on the two time intervals of some tj and tj plus 1, then the corresponding equation the corresponding formula is called as the two level formula. Or when suppose if you are using the some methods which is having the three different levels, that means the t of j minus 1, tj and tj plus 1. Suppose if your equation is actually having all these three coefficients of the j minus 1, j and j plus 1, then they are called the three level formula. Okay, so first we look into this explicit method to solve this the heat conduction equation. So in the explicit method, you are going to find out what is the u of t as well as the u of xx. That is what the coefficients which is the values which you are using in the heat conduction equation. So which the t is actually varying in the j is the incremental value for the t, so that I can write this dou u by dou t. We can write this in the using the finite difference method. U of I comma j plus 1 minus u of I comma j divided by this delta t. So this delta t is nothing but the increment in the let us take it as a k, because in y-axis we are actually varying with respect to k. So the two different consecutive intervals between the ti and ti minus 1 can be taken as a k. Okay. Similarly, for the second order difference equation for this u of xx, we can use the central difference approximation method, means dou squared u by dou x squared, which is equal to u of I minus 1 comma j plus u of I comma j, means minus 2 times of u of I comma j plus u of I plus 1 comma j, the whole divided by delta x squared. So delta x is actually varying with respect to h, so I can take it as a h squared. So these are all the two equations which we are going to use to solve this heat conduction equation. So I can just solve substituting these two values, two expressions into this heat conduction equation, so that I can write u of t, which is equal to c squared into u of xx. So that is the heat conduction equation. So I can just substitute the values of u of I comma j plus 1 minus u of I comma j divided by k, which is equal to some c squared into so u of I minus 1 comma j minus 2 times of u I comma j plus u of I plus 1 comma j divided by h squared. So I can take this h squared here, so I can write this as the h squared. And since this k is not equal to h, we always have the rectangular type of mesh point. So I can just divide this equation by divide by the k. That means multiply this whole equation by k, so that I can get u of I comma j plus 1 minus u of I comma j, which is equal to k times of c squared divided by h squared u of I minus 1 comma j minus 2 times of u of I comma j plus u of I plus 1 comma j. Now I know this k and h values, and see everything is as a constant value, so that I can define this equation, this constant value as lambda. This lambda is nothing but the mesh ratio parameter. So that I can just rewrite this equation as u of I comma j plus 1 minus u of I comma j, which is equal to some lambda into u of I minus 1 comma j minus 2 times of u of I comma j plus u of I plus 1 comma j. Now I can just rearranging or combining all the coefficients of u of I comma j. So the final equation I can write as u of I comma j plus 1, which is equal to some lambda iso into u of I minus 1 comma j plus 1 minus 2 times of lambda u of I comma j plus u of I plus 1 comma j. Okay, so this is the final equation which is known as the Schmidt equation or explicit method, which is used to solve this heat conduction equation. Okay, so if you want to find out the value of temperature at j and I plus 1 levels, you require the values of u values at I minus 1 j and I comma j and I plus 1 comma j, so that this Schmidt method can be visually represented as, so the value of u of I comma j plus 1 at this point is actually identified using this previously calculated values of the previous level of this j value, that is the nodes which we have calculated using the I minus 1 j, ij and as well as the I plus 1 j. So if you know this all these values, then you can find out this I comma j plus 1 value using this Schmidt formula. So now I am going to solve this heat conduction equation using this Schmidt method, and with just explain the one example problem. The example problem is, so to solve the heat conduction equation, u of t is equal to u of xx with the limits of x value, limit of x having the values of 0 to L, with the value of u of x comma 0 is equal to sine of pi x, and the x value of this is actually again runs from 0 to L. The initial conditions are given as u of 0 comma t and the u of 1 comma t, which is equal to 0, that is the boundary values, using the Schmidt method. Assume that the time step of h is equal to varies from 1 by 3. So we have to compute the solution at lambda is equal to 1 by 2 with the time steps of 2, and the lambda is equal to 1 by 4 with the 4 time steps, as well as lambda is equal to 1 by 6 for 6 time steps. Suppose if the exact solution of the corresponding equation is given as u of x comma t is equal to e power minus pi square t into sine of pi x, we have to compare the solution at the time of t is equal to 1 by 9. That means you have to compare the numerical as well as the exact solution, and we have to write, we have tabulated the error values for all the three lambda values. So we are going to use the Schmidt method to solve this equation. So the Schmidt method equation, which I can written as Schmidt method equation, which we have derived, is u of I comma j plus 1, this is equal to lambda times of u of I minus 1 comma j plus 1 minus 2 lambda u of I comma j plus lambda times of u of I plus 1 comma j. So the value is given as h is equal to 1 by 3. So each time step the value of h, that means in the x axis, the time step is actually varying with respect to every 1 by 3 times for each and every increment. Therefore, the nodal points of this equation can be given as, so the schematic representation of the mesh points is given here. So initially the starting value of value is 0, and this L is given here. This is the boundary condition is given as 1, and in the value, so which is varying with respect to the time step of 1 by 3. So the first time step is actually varying from 1 by 3, and then plus 1 by 3, then again plus 1 by 3. You will get the mesh points in the x-axis, and for each mesh point we have to find out the we have to find out all values in terms of the jth corresponding jth interval. So we have to find out the solution of the two interior points at 1 by 3 and 2 by 3. So the initial conditions are given as, the u of x is given as 1 by 3 and y is given as 0, which is equal to u of 1 comma 0, and can be written as, so the function is actually given as the sine of pi x. The function is given as u of x comma 0 is given as sine of pi x. So I can just substitute the values of x value here. So sine of pi into x is nothing but the 1 by 3, so that I can given as sine of pi by 3. The value of sine of pi by 3 is given as root 3 by 2. And similarly, you can find out the initial condition at this value of the x of 2 by 3. So u of 2 by 3 is given 0, which is equal to, the numerical solution is 2 comma 0. That can be written as again sine of 2 pi divided by 3, because 2 by 3 is the h value. So if you find the values of the sine 2 pi by 3, which is again having the values of root 3 by 2. So these are all the initial conditions. So the boundary conditions are given in this equation itself, because it's a u of 0 comma t and u of 1 comma t which is equal to 0. So the boundary conditions given is u of the boundary condition given as u of 0 comma j which is equal to 0. Similarly, the u of 3 comma j, that means that the next every I value is actually incremented by 1, 2, 3, and then the u of 3 comma j, which can be also given as a 0 for all the values of j. Okay. Now first we are going to consider lambda is equal to 1 by 2, and we are going to do the 2 time steps for this lambda is equal to 1 by 2. Suppose if you substitute the lambda is equal to 1 by 2 in the Schmidt equation, then the equation becomes u of I comma j plus 1, which is equal to 1 by 2 times of u of I minus 1 comma j plus u of I plus 1 comma j, where j stands from 0 and 1 and I is also runs from 1 and 2. Okay. So these are all the for the 2 points which we are going to find out the solution for lambda is equal to 2. So for j equal to 0, how to find out the solution as I equal to 1 as well I equal to 2. Suppose if you substitute these two values here, so u of 1 comma 1, which can be written as this can be written as 0.5, so 1 by 2, and so I value is generally given, so 0 comma 0 plus u of 2 comma 0. So values of 0 comma 0 and 2 comma 0 is already given, so 0.5 times of 0 comma 0 is nothing but 0 plus u of 2 comma 0 is given as this root 3 by 2. Suppose if you find out the root 3 value, the number and the value of root 3 by 2, which is actually given as 0.866 to 025, that is the value of root 3 by 2, so that the final value of the u of 1 comma 1, which is equal to 0.433013. So that is the value of u 1 comma 1 for the I equal to 1. Similarly, I can find out the value of I is equal to 2. This can be written as u of 2 comma 1, which is equal to again 0.5 times of u of 1 comma 0 plus u of 3 comma 0. Okay. Again, the values of the 1 comma 0 and the 3 comma 0 is actually substituted here 0.5. So 1 comma 0 value is again the value which we have calculated, that is root 3 by 2. So that I can write the value of root 3 by 2 0.866025 plus 3 comma 0 is given as 0 from this boundary values. So the final value is again same value 0.433013. So the value of u11 and u21 having the same values for I is equal to 1 and I equal to 2, for j equal to 0. Similarly, we can repeating the same steps for I equal j equal to 1. For j equal to 1, again we have to find out what is the value of I equal to 1 as well as I equal to 2. So this value is given as 1 comma 2, u of 1 comma 2, which can be given as the equation 0.5 into the u of 0 comma 1 plus u of 2 comma 1. So this is the values once we substitute j values and I values in the main equation, and you know the values of 0 comma 1 as well as the 0 2 comma 1 from this the previously calculated values. And if I substitute the values of 0 comma 1 and u of 2 comma 1, the final value will be 0.216507. So that is the value of u of u 1 comma 2. Similarly, I is equal to 2. We have the u of 2 comma 2, again 0.5, u of 1 comma 1 plus u of 3 comma 1. So again we know these values of this 1 comma 1 as well as 3 comma 1. So 3 comma 1 value is 0 and u comma 1 comma value which we have calculated previously. Substitute the values, the final value will be equal to 0.216507. That is the value of u of 2 comma 2. Okay. Therefore, after the 2 time steps for j equal to 1, I equal to 2, for lambda equal to 2, we have the t is equal to 2 times of k, because I is taken as j is taken as 2. That is actually given as 1 by 9. Okay. Because we already know this mesh ratio parameter as c squared k divided by h squared. Here in this equation the c squared value is 1, because we have the value of a u of t equal to u of xx. So the c squared is actually equal to taken as 1. So c squared is given as 1, and the value of h squared is actually 1 by 9 times of sorry, 1 by 3 the whole square, so that I can get the 1 by 9 for this t, so that I can find out the values of u of 1 by 3 and the time value is 1 by 9, which can be easily equation given as this u of 2 by 3 comma 1 by 9, that is nothing but the value which we have calculated here, 0.216507. Okay, so this is the value of the time t is equal to 1 by 9. So in a similar way, we can calculate the second section, that means the second point, where lambda is equal to taken as 1 by 4, and we have to do for the 4 time steps. That is for j is equal to 0, 1, 2 and 3. So for that values, you have to find out the values of each and every j value. You have to find out the values of I is for 1 and 2. So suppose if you have this lambda is equal to 1 by 4, therefore the h is equal to, we already know this, h is equal to 1 by 3, and so then therefore we can find out the k value. So k is nothing but the lambda times of h squared from this mesh ratio parameter, so that I can just substitute the values of lambda and h. You can get the value of the k is equal to 1 divided by 36. So that we have to do the computation for the 4 time steps, that is up to t is equal to 1 by 9 for lambda is equal to 1 by 4, so that I can rewrite the same Schmidt equation for this lambda is equal to 1 by 4, which is given by u of I comma j plus 1, which is equal to 1 by 4 times of u of I minus 1 comma j plus 2 times of u I comma j plus u of I plus 1 comma j. Okay, here this j is actually runs from 0, 1, 2 and 3 for the 4 time steps. Similarly, I is actually runs from 1 and 2. Okay, for therefore we have to find out the value for the j is equal to 0 to 3, for I equal to 1 and 2. So suppose if you find the for j is equal to 0, I equal to 1, so we have the values of u of 1 comma 1, which is equal to, I can just substitute the values of j and I and j values in this equation. I can get 0.25 because it's 1 by 4, and this value is given as u of 0 comma 0 plus 2 times of u of 1 comma 0 plus u of 2 comma 0, so that I can just given the values, the initial value 0 comma 0 is given as 0 plus 2 times of u of 1 comma 0, which we have calculated is 0.860025 plus u of 2 comma 0 is also 0, so that the final value is equal to 0.649519. So that is my u of 1 comma 1. Similarly, for I can do it for the I is equal to 2, so the u of 2 comma 1 can be written as 0.25 times of u of 1 comma 0 plus 2 times of u of 2 comma 0 plus u of 3 comma 0. So if you substitute the values of u1 comma 0, 2 comma 0, 3 comma 0, and if you do the mathematics of the final value is 0.6495, sorry, 649519. So that is for the value of 2 comma 1. That is for the j equal to 0. Similarly, for j is equal to 1, again we can calculate the values of y equal to 1 and I is equal to 2. So if I take I equal to 1, the values of is 1 comma 2, which is equal to again 0.25 times of u of 0 comma 1 plus 2 times of u comma 1 comma 1 sorry, plus u of 2 comma 1. And substituting the values of these values, the final value is given as 0.487139. And similarly, you can calculate y equal to 2, u of 2 comma 2, which is again equal to 0.25 of u of 1 comma 1 plus 2 comma 1 comma 1 plus 2 times of u 2 comma 1 plus u of 3 comma 1. So again substituting the values, the final value is given as 0.487139 for the same value for the u of 2 comma 2 also. So if you are doing it for repeatedly for j is equal to 2, again you can take the values of I equal to 1 and I equal to 2. So the value of u of 1 comma 3 and u of 2 comma 3 can be finally calculated from the same formula, I'm just giving the final values only. So 0.365354, and similarly T, 3 also having the values of 0.3653 and 54. And finally for j is equal to 3, again we have to find out the values of I equal to 1 and I equal to 2, which can be written as u of 1, 4 and u of 2, 4. And the values of this 1, 4 and 2, 4 given as 0.274016, and similarly this is 274016. Now we have calculated the values for I equal to j equal to 0 to 4. Now I can find the t is equal to 4 times of k, which is equal to 1 by 9. Therefore the exact solution, the numerical solution is 1 divided by 3, 1 by 9. There is value of x and y, which is equal to u of 2 by 3 times of 1 by 9, because both the values of 1 by 3 times as well as 2 by 3 times are equal, which is equal to 0.274016. Okay. So in a similar way, you can do it for the lambda is equal to 1 by 6, the third section, lambda equal to 1 by 6. So the schematic equation for this can be written as u of I comma j plus 1, which is equal to 1 by 6 times of u of I minus 1 comma j plus 4 times of u of I comma j plus u of I plus 1 comma j, where this j is actually running from 0, 1, 2, 3, 4 and 5, and I is running from 1 and 2. Suppose if you calculate substitute the values for all these values for each and every case like the previous values, the final value I can just written as the u of 1 by 3 comma 1 by 9, which is equal to u of 2 by 3 comma 1 by 9, which can be written as 0.29000031. So this is the value for lambda is equal to 1 by 6. Okay. So we have the values for all the three lambda values. Lambda is equal to 1 by 2, 1 by 4 as well as 1 by 6. So that suppose if you find out the error for the exact solution, the exact solution is already given. So that for I t is equal to 1 by 9. So the exact solution is given as 1 by 3 comma 1 by 9 and u of 2 by 3 comma 1 by 9. This is equal to the exponential of minus pi squared divided by 9 into sine of pi by 3, because the value of t is given as 1 by 9. So the final value of the exact solution is given as 0.289250. Okay. So this is the exact solution. So that I can just compare this exact solution with the numerically calculated solution. For lambda is equal to 1 by 2. We have the solution as absolute value of the numerically calculated value 0.216507 minus the exact solution 289250, which is equal to 0.072743. That is the error calculated for the lambda is equal to 1 by 2. Similarly, lambda equal to 1 by 4. We have the numerically calculated solution as 0.274016 minus the exact solution is 0.289250. This is equal to 0.015234. And finally, for lambda is equal to 1 by 6, we have the exact solution. The numerically calculated solution is 0.290031 minus 0.289250. That is equal to 0.000781. Okay. So therefore, the lambda value is decreased further, then the accuracy of your solution will increase further. Okay. So which is almost like the time step. So in this way, you can easily solve any heat conduction equation using this explicit method. Whatever the values, whatever the equations given, the heat conduction equation given, you can solve it using the Schmidt or explicit method. So in the next video, I will explain how to solve this the heat conduction equation using the Crank-Nicholson method. Okay. So stop here, and if you have any doubts, then we can clarify in the online class. Okay. Thank you.